So if you remember, we said that it's difficult to plastically deform the material if you have polycrystalline material compared to single crystalline material. Now, in single crystalline material, if the applied stress is high enough, then what's going to happen? If the applied stress is high enough, then that applied stress will result in a certain shear stress, and that shear stress will be able to activate certain plane inside the material. So the dislocation can slip on that plane to a certain direction, right, until it hit the surface of the specimen. And that will result in some changes. We call, we're going to see steps on the surface here, right? So that deformation, plastic deformation, it's much easier if you look in, if you're going to compare it with the polycrystalline material, because when we deal with polycrystalline material, what we have, well, we have, if this is a polycrystalline material, right, and you are applying, let's say, a tensile load in a certain direction, right? So what's going to happen here if we apply a tensile load? Well, if a certain grain is favorably oriented in a way that will activate its slip system, then let's assume this grain here start to activate first. The dislocation will start to slip on that plane. So what's going to happen if this dislocation hit the grain boundary? Now we are having an issue here because you have this continuity of the slip plane, right? So you need to supply additional energy in order for the dislocation to cross the boundary to another grain. Also, the other issue, because you have different crystallographic orientation of these grains. So, so what's going to happen if this is the slip plane on this plane, on this grain, then maybe the slip, the one that will be activated first in this grain, maybe it's going to have different direction. So that means the dislocation not only it needs to cross the boundary, but also it has to change its orientation in order to continue slipping on the other slip plane. So it is why it's difficult to plastically deform the material compared to single crystalline material, because here, in order to have plastic deformation, is not enough only to activate a single grain. Well, we have to activate the other grains also, right? And because those grains also, the grain balance cannot be broken, so you cannot break it, the grains, right? So what's going to happen? Each grain will be constrained by its neighbors. When the next neighbor will start to activate, what kind of shape the next neighbor it has. So there will become some constraint that will increase the needed stress in order to deform such material. This is why if you do plastic deformation to the material, you're going to take it from this state to the see here, we have equiax grains, so the grains might have the same direct dimension in all directions, to after plastic deformation to elongated strain, as you can see here. If you're applying a tensile strength in this direction, then those grains will be elongated on the direction of the applied stress. Okay, so they will be elongated on that direction. This is better to maybe to represent it by something something like this. So it will be elongated in the direction of the applied stress. So the result of plastic deformation is we are elongating the grains of the material. Okay, so the message from this slide: it's difficult to plastically deform the material, and what's happening as a result of plastic deformation, we are elongating and deforming the grain shape that we have here. So the question that we had in the previous lecture that we tried to answer, how can we make the material stronger? Because as a materials engineer, I think you want also, in some applications, you want to increase the strength of the material. So how can I increase the strength of the material? This is a very important question. And in order to think about mechanisms or approaches, you need to know what is the goal that you want to have, what you want to do at the end by those different mechanisms. Because identifying the goals will help you to, wisely pick the right mechanism that will take you to that goal. Now, as a reminder, we say that plastic deformation, plastic deformation will happen, will be initiated if the dislocation is able to slip. So that means if we can slip dislocations, right, then we can have plastic deformation, right? And if we want to increase the strength of the material, that means we don't want the material to deform. Or we want to make it's much difficult to deform the material, plastically deform the material. So that means if you want to make this as difficult, then you have to make this to be also, if you want to make this to be difficult, plastic deformation, then you have to prevent the movement of dislocation. So the goal is we want to reduce dislocation mobility. We want to place more restriction in the front of the dislocation. So it's going to need higher stresses in order to initiate the plastic deformation. This is why in the previous lecture, what we did, we went through 3 different mechanisms. Those mechanisms will allow the material to gain more strength. So grain size reduction, solid solution alloying, and strain hardening of the material. If you go to the first one, the grain size reduction, right? So as the dislocation is moving, so now having this dislocation is slipping on a certain plane to a certain direction, right? And once it hit this grain boundary, as I mentioned, now this plane is not, continuing anymore and throughout the grain boundary. So we have some discontinuity there. And also, this is the slip plane or the active slip system on this neighbor grain, adjacent grain, right? So what's going to happen now? The dislocation first, it needs now additional energy to cross the boundary, the grain boundary, and thus this additional energy to change its orientation, its direction from being in this direction to change to this direction. And you can imagine if the misorientation between the grains is higher, then the changes in the direction will be much higher. If the misorientation or mismatch between the 2 grains is smaller, that means the changes in the orientation that this location needs going to be much smaller. Let me take you to the next slide here. If you remember in the previous lecture, in chapter 6, we talked about something called low angle. We talk about something called low angle grain boundary and high angle grain boundaries, right? So here in low angle grain boundary, there is no much, difference in the crystallographic orientation of these 2 grains. However, if you look at these 2 grains, there is a big mismatch in terms of the orientation of these 2 grains. We call it high angle grain boundary. Now, you can understand that having small angle grain boundary, when 2 grains, they don't have that big, differences in the crystallographic orientation, then that will not place much obstacles in the front of the dislocation compared with the high angle grain boundary. And if we have high angle grain boundary, actually, what's going to happen? It will be very difficult to dislocation to change this, from one direction to the other direction. So what's going to happen? Actually, we'll have, as we mentioned earlier, we're going to have a pileup of dislocation here. Okay, you're going to have, let's say, a pileup of dislocation that cannot move to the other grain. And the reason they cannot move to the other grain, because there is, dislocation had to change its orientation by a large degree, or maybe this is still not active yet. So what's going to happen? This pileup of dislocation will act as a stress concentration that will initiate new sources in the other grain. The message from this, what you need to know from this, is grain boundaries will has its own effect on the strength of the material, because you can place more obstacles in the front of the dislocation, and those dislocations might not be effective if you have low angle grain boundary. And if you look at the yield strength of the material, we can increase, or we can correlate between the yield strength of the material and the average grain diameter of the material. Here, if you look at this figure, the yield strength of the material versus the grain size diameter. Now, as you increase the grain diameter, then you're going to have less surface area, or smaller grain boundary surface area, right? So what's going to happen? If you increase, so here the diameter will increase from right to left. If you increase the diameter of the grain, what's going to happen to the yield strength? It will decrease, right? So if you increase the diameter of the grain, okay, what's going to happen to the yield strength? It will decrease. It's going to be easier to plastically deform. However, if you decrease the diameter, so you have finer grains, what's going to happen to the yield strength? It will increase. Now material becomes stronger. And why it becomes stronger? Because now we have more grains, more grain boundaries, and we have more restriction in the front of the dislocation. Now this equation is a very good equation. It's called Holbich equation, and this equation can allow us to correlate between the diameter of the grain and sigma, the yield strength of the material. Now, this cannot be applicable to very, very, very fine grains, and also not very coarse grains. So these are materials constant. So what we can learn from this first mechanism is, if you control the size of the grain, then you can increase the strength of the material. Then we move to the second one. It's called solid solution strengthening. If you remember, in the previous, in chapter 6, when we talked about the, if you remember, when we talked about the defects inside the material, the impurities inside the material, we said we can tune the properties of material by adding impurities to the material. So there is a certain motivation for us to add impurities to the material, right? And we can change, it turned out we can change the mechanical property. We can make material stronger by adding impurities to a certain material. So solid solution is a way to make the material strong. It's why it's called solid solution strengthening. If you have a system where you have a copper and you want to add to it nickel, okay, and you look at the tensile strength and the yield strength of the material, okay, you want to see what's going to happen. So we got a copper, pure copper, 0% nickel at this point. We got pure copper, okay. So pure copper has maybe around 220 megapascal, right? So let me write it here. So maybe we got here 220 megapascal, right? So this is the value of the you know 0% nickel. Now, what's going to happen if you make a material that is composed of 30% nickel? Okay, so 30% nickel. So you're going to take 30% nickel, 70% copper. You can see that you can increase the tensile strength of the material. You're going to take it from 220 all the way to something around 300, something around 300, maybe 70 megapascal, right? So you can take it from 220 all the way to uh, uh, 370 megapascal only by adding those impurities. Similarly, when you look at the yield strength, you can increase the strength by tremendous amount. You can take it from around 60%, from 60 megapascal all the way maybe to 160 megapascal if you got 50% nickel. The challenge here is solid solution will increase the strength of the material, but the challenge is if you increase the strength of the material, you're going to sacrifice the ductility. So this figure is showing the elongation, so it's expressing the ductility in terms of the elongation percentage, and you see that as you add nickel, if you have nickel, if you add nickel, what's going to happen? You're going to decrease the ductility of the material. Now the question: why the strength of the material? Why the material is increasing in terms of its strength as you are adding those impurities? And to answer this question, you need to see what's happening as a result, as a consequence of adding those impurities to the material. When you add impurities, there are two possible scenarios. Either you got something, the impurity that you are adding, it has smaller diameter, right? So what's going to happen? This atom will push the neighbor atom. So that's going to result in a tensile strain. However, if you look here, the second case, what's going to happen? This larger atom will result in compressive strain field in the neighbor around it. Okay, so for the adjacent atoms. So this result in tensile strain field is going to result in compressive strain field. Now, what I want you always to remember, the material always do its best in order to minimize its state of energy. So if a certain material has this state of energy, and there is a way to minimize that energy to a lower state of energy, then what's going to happen? The material will utilize whatever resources available in order to move from state A to state B, which has lower state of energy. And the more that you lower the state of energy, right, the more stable is the material, then it will be much difficult to take it from that level to higher level. So if you look now at this, the first party, what's happening, this is going to result in tensile field. But also we know that if a material has dislocation, or materials they have dislocations, there is a certain strain field associated with the dislocation. So in top of the dislocation, we got compressive, okay, and below the dislocation, you got tensile. In top of the dislocation, you got compressive, and here you got tensile. So what's going to happen if you try to if you are add impurities to the material? Well, the material will say, now I have some resources, some help that will allow me to lower my state of energy, to move from state A to state B. And to do so, what's going to happen? Those smaller atoms will reside in top of the dislocation, and since this will result in the impurity will result in tensile strain field, and there's a compressive strain field. So these two might cancel each other, right? And similarly, these two might cancel the compressive and the tensile might cancel each other. So the result of this, you can reduce the strain field that was there around the dislocation by doing so. So you can move from state A to state B, and you can imagine if you do that, then the material become now more stable. It will be difficult to take it back to state A where you have higher state of energy. So so solid solution will help in increasing the strength of the material. The third type is called strain hardening. Okay, now here is strain hardening. What we will do, we plastically deform the material, and during the plastic deformation, we are increasing the density of the dislocation. We are activating more slip systems so the dislocation can move. And if we compare two scenarios, let's take scenario number 1, scenario number 2, okay? And let's imagine you're applying a certain shear stress, right? So what will happen? Well, let me delete this. Okay. And then let me draw this. Okay, so this is scenario number 2, and and you're applying a shear stress. Okay. So in the first scenario here, in the first case, what you got? You got a dislocation that is moving on the slip plane. For sure, you need smaller amount of stresses compared to this situation where you got more dislocation active to move, right? So here, the needed stress will be less than the stresses that's needed in this case. So as you do cold working, you're increasing the density of the dislocation, or activating more dislocation, more slip system inside the material. So strain hardening, you can call it also, you can work hardening or cold working, as I mentioned in the previous class, that and for most metals, because this kind of deformation is happening in room temperature, so this is relatively cold compared to the melting temperature. This is why it's called cold work. So cold working, work hardening, strain hardening, it's referring to the same thing, which is you plastically deform material, and then by doing so, you are increasing the density of dislocation, and as a consequence of this, you increase the restriction in the front of dislocation, and as a consequence of this, you're going to prevent more and more plastic formation, and the result of this, you need higher stresses from outside in order to plastically deform the material. Now, the cold working can be quantified by using this equation, where we consider the changes that we might see in the dimension of the material. This equation can help us to quantify the reduction in the area as a consequence of the plastic deformation. Now, if you look at the mechanical properties of the material, what's happening as you as you cold work the material? So here we have 3 figures. The first one is about the yield strength of the material and the tensile strength of the material, and your percent cold working, percent cold work. Now we have copper, brass, and then you have the steel. For all different materials, the more cold work you do to the material, as you can see, the increase or the improvement in the strength of the material. Let's take an example here. For example, let's take this example. Let's take the steel. So the steel you have around 450. So you started with around 450 megapascal. This is the yield strength of the steel. So if you take a fresh specimen that that hasn't been plastically deformed before, and so at the beginning, the yield strength will be around 450. And then if you do 10% cold working, so what's going to happen? So 10% cold work going to result in around 700 megapascal. Okay, so you can see how much you can improve the strength. You can take it from 450 all the way to 700 megapascal. Similarly with other material. So what we can learn from this is, as you do more cold working, as you do more cold working, what's going to happen? Well, you're going to increase the strength of the material, whether it's the yield strength or the tensile strength of the material. But also we learned before, if you increase the strength of the material, you will be losing something. You're going to sacrifice something that is very important as a mechanical property, which is the ductility of the material, right? So if you look at the ductility represented in elongation percentage, you see that the more cold working you do, the more that you're going to reduce the ductility of the material. And if we take this example, if you take these, if you look, for example, steel, in the beginning, you got something around 25 megapascal or 28 megapascal, sorry, 25 percentage of elongation. And if you do only 10%, if you do only 10% of cold work, what's going to happen? You're going to reduce that to around 18 or 16% of elongation. So the more cold work you do the material, okay, you will enhance the strength of the material. At the same time, the material become more and more brittle. So you're losing ductility of the material. So at a certain point, as you're losing ductility, the material will break all of a sudden. If you remember that the graph that I showed you in the previous lecture, right? So this is this is the same material, and what's happening if you do cold work every time, what's going to happen? So let's say this is 0% cold work, this is 10% cold work, and this is 20% cold work. What's happening? You are increasing the strength of the material. At the same time, you're reducing the amount of plastic deformation the material can entertain. So the consequence of this, material become more brittle, so it's going to break earlier. Okay, good. So, and then we finished the discussion of the strengthening mechanism, and now we are left with a big problem, and that we have to a big problem on the table that we have to come up with a solution to it, which is imagine that in the beginning you only want to change the shape. You want to change the shape of a material. Okay, let's say in the beginning, this is the first case. All what you want to do, you want to change the dimension. Okay, you want to change. You have some delta in the dimension. Okay, you want to change some dimension. But if you change the dimension, the second case, all what you want to do is you want to increase the strength of the material. Okay. Now, in both cases, what's happening, if you change the dimension, permanently change the dimension, if plastically deform the material, the consequence of this, even if you don't want that to happen, but it will happen, okay? The consequence of this, you will increase the strength of the material. And also the consequence of this is you're gonna decrease the ductility of the material. So what happened? This will increase, and this will decrease, right? Also, imagine in the second case, you want to increase the strength of the material. You found that this material is not strong enough, and then you look at different mechanisms, and you learn that if you plastically deform the material, you do cold working, then what's going to happen? You can increase the strength of the material. Okay. Now the issue is by doing so, you will lose some ductility, right? Again, so you're going to lose some ductility of the material. You're going to lose some ductility. So in both cases, whether case number one or case number two, we are having an issue is how we can, get some ductility back to the material, right? Because we want that ductility in many engineering applications. You want the material to show some, ductile performance behavior, to become, to show some ductility, because you don't want the material to break all of a sudden. Because if it has a brittle nature, then if it has a brittle nature, then it's going to break all of a sudden. It cannot, entertain more deformation. So the question that you have is, okay, then what we're going to do? What we're going to do in both these cases, how we can, gain or regain ductility back to the material. And it turned out it's not something that's very difficult, but something that needs someone to do it in a wise way. Because remember, if you gain ductility again, you will lose strength. So this is why, at the end, it is the decision of the material engineer to decide what is the optimum, what is the needed stress and ductility for a certain application. Okay, so there is no right or wrong here. What determines right or wrong is the application itself. Okay, where the material, the environment at which the material will be exposed to. So that will determine what is the optimum, what is the needed, the minimum stresses that is needed. Okay, and the ductility that is needed for the material. And it turned out, in order to gain back some ductility, it turned out there's something called annealing, which is it's a heat treatment process of a material. So in the heat treatment process, what we are doing, we are heating up the material. So we are taking the material, let's say, from T1, okay, all the way to T2. So from T1 to T2. So we are providing some heat to the material in order to gain some ductility to the material. Interestingly enough, it turned out as you heat up the material from T1 to T2, what's going to happen? Well, the material will not go from one state to another state all of a sudden. It turned out there are phases that the material will go through as you are heating up the material. And those phases are the recovery. Okay, so 3 phases: recovery, recrystallization, and then it will end up with the grain growth. Okay, so 3 possible phases. The first one, recovery, recrystallization, and then grain growth. And what we will do in the remaining minutes, we will try to get more information, learn more about the recovery stage, what's happening during the recovery stage, and the recrystallization stage, the grain growth, and then how this will affect the mechanical property, and more specifically the tensile strength and the ductility of the material. Okay, so if you go with the first stage here, the first phase called the recovery. Okay, so recovery. So what we do during the recovery stage, the goal of the recovery stage is to minimize the energy of the material. Remember what we said earlier. We said that if a material is in state A, always the material will ask itself the following question: can I minimize my energy to state B? So this is state A, this is state B. And if you start to, as I mentioned in the beginning of this lecture, if you start to provide some, some resources to the material, some help to the material, that help could be in terms of energy, like in this case, right? If you are heating up the material, so what's going to happen? The material will utilize this energy in order to move from state A to state B. And to do so, as you're heating up the material, the atoms will be energized to diffuse from one position to another. So what's going to happen? The material would reorganize itself, right? Will reorganize itself in order to minimize energy to go from A to B. So what's going to happen? So what could happen? Either one or two. For example, dislocation configuration with the low strain energy. What does that mean? We know that for this dislocation, there's associated compressive strain field and also there's associated tensile strain field, right? And the material will say, if I can align those dislocation underneath each other, then what's going to happen? The compressive that we have in top of the dislocation will kind of cancel or reduce the effect of the tensile field that we see here from the above dislocation. And similarly here, the tensile here will be reduced or eliminated by the one here. So the message here, by having a certain configuration of dislocation, having them align underneath each other, that might reduce the strain energy that associated from this dislocation. So one thing the material can do during the recovery phase is to bring dislocations underneath each other to have a certain configuration with them that will lower the strain energy, so it can help the material to go from A to B. The second possible scenario is, imagine you got a dislocation, and there is another dislocation here. Okay, so what we have in top of the dislocation? Well, we have atom, extra half plane of atom in top of this dislocation, and we have here extra half plane of atom of this dislocation. And between these dislocation, we have empty space, right? So the material will say, now, if I have enough energy to move atoms, okay, from different places, we don't want to answer the question from which places, but let's say if the material will say, if I have enough energy to move atoms from the material from different places, okay, to bring them here, okay, where you have a vacant position, then what's going to happen? Well, those atoms will fill those vacant positions, and the result of this, you're going to annihilate the dislocation that you have over here. So as a consequence of this, you reduce the number of the dislocation that you have. So this is scenario number one. Scenario number two, or the first case, what you can have, imagine you got a dislocation that is slipping on this plane. Okay, so dislocation is slipping on this plane. And this dislocation is facing another dislocation in the front of it. And there's an obstacle, right? So dislocation, to see another dislocation, is an obstacle here. It wouldn't be easier as if the dislocation is sliding or slipping on a plane that has less number of dislocation. So if you provide heat to the material also, by having heat, it can diffuse vacancy, right? So we know that in top of this dislocation, we have atoms, right? Now what we can do, the vacancy inside the material will diffuse from different positions to in top of the dislocation. And if vacancy diffuse here, then if you have a vacant position here, what we have done to the dislocation, actually we push it to the top. So now the dislocation become here, where you got here underneath it, you got vacancy, right? So we let the dislocation to climb from one plane to another plane. Now maybe on this plane there is no dislocation, or there's less density of dislocation, or maybe also it can face another dislocation with opposite signs. So when they come together, they will cancel each they cancel each other. So in both these two cases, we can reduce the dislocation number within the material. So what's happening during the recovery stage is we are reducing the dislocation number or lowering the strain energy. The goal is we want to go from A to B. But what's happening in this stage is not enough to change the mechanical property of the material. So this, what's happening here could affect the electrical property, the thermal property of the material, but in terms of changes in the ductility and the strength, it will not be that significant. It will not be significant until we go to the next stage. Now, in the next stage, it's called recrystallization. Now, in the recrystallization, what's happening, if we continue to reduce the dislocation density, now imagine you got this grain, okay? So this is the initial grain. It's highly strained grain. It has many dislocations, right? Because as a result of the cold working, right? So you got many dislocations there, right? So, and then if you start to provide heat, as we mentioned in the previous phase, you start to reduce those dislocations in some regions, right? Now, what's happening during the recrystallization, you're gonna start to form region. And those regions, they are strain-free regions, okay? So you start to initiate small regions within the highly strained region, and those regions, they have much less number of dislocation. They have strain-free regions, and then they will start to initiate them. And what's going to happen as the time progresses, or as at high temperature, what's going to happen? Those regions will start to grow further and further until they consume the parent material. So the result at the end of the recrystallization stage is we're going to form new set of strain-free and equiaxed grains. So the idea is, at the end of the recrystallization, we're going to take the material, the polycrystalline material. We're going to take it back from elongated grains all the way to the situation before we have done any cold working to that material. So this is how it looks like before cold working, equiaxed grains. Now, when we apply some cold working, we took it to elongated strains, right? So this is the result of cold working, and this is the result of annealing the material, right? So when you do the recrystallization, what's going to happen? By increasing the temperature, you're going to take it back to equiaxed grains. So the goal is we're going to take the polycrystalline material from this state to this state. So the result at the end of the recrystallization stage is what we are doing. Actually, we are taking the material back to take its original shape for the grain. Let's give a closer look to what's happening to the material. Okay, so this is a polycrystalline material, and so this is a cold work material. So you have done 33% cold working. And what you can see, so this is a grain, and this is another grain, this is another grain, this is another grain. You can see those lines representing, it's called dislocation. So the dislocation line was activated on the slip system inside the material until they approach the surface. So this is how they look like after they approach the surface. Okay, so if you start to apply some heat, what's going to happen? You start to initiate, you see black dots over here, small black dots. If you start to apply heat during the recrystallization step, you will start to form regions, new regions that has less strain energy. Let's call it strain-free energy. And what's happening if you continue supplying the heat? Well, those small regions will start to grow and grow until they completely replace the mother, or sorry, the parent material. Okay, so they will consume the original material. So now you get rid of all the highly strained material, and now you form a material with equiax grain with strain-free energy compared to the cold work one. So what's going to happen? So now the material is very happy because the material, by using the heat that you provided to it, it uses it to reduce the strain energy. But if you continue supplying heat to the material, remember, always the material will ask itself, now if I am in state A, now I want to B, is there a way to go to C? Is it possible to go to C, right? So this is A, and now this is B, is the way to go to C. Now, if you continue supplying heat to the material, what's going to happen? Well, the material will try to utilize that heat to reduce the grain boundaries that is there, right? So how to reduce the grain boundaries is by growing each grains, by growing the grains, right? So if you grow, it's called grain growth stage, where you can grow the grains to have less grain boundaries compared to this situation. Because remember, in the chapter, one of the previous chapters, we talk about the defect, we say that there is an energy associated with each type of defect, right? So with a point defect, or the dislocation, or the grain boundaries, or the external surfaces. So what's going to happen? The material, it will grow, and that growth can be quantified, and we can control it. And we're going to talk about this in the previous lecture, in the coming lecture. Also, what we're going to talk about in the coming lecture, we're going to see what is the needed temperature to do the recrystallization, and how the recovery, recrystallization, grain growth, both will have its effect on the mechanical property. So I will stop here and see if you have any questions.